we've got Professor Brett Sanders from UCI with us, and he's going to be talking about flooding in the Los Angeles basin. And flooding and erosion have emerged as one of the greatest climate challenges facing the world today. Losses are escalating at an alarming rate, and millions of people are impacted by flooding every year. At the UCI Flood Lab, Professor Sanders and his team advanced simulation technologies for characterizing flooding and erosion dynamics, and join multidisciplinary research teams and work with affected communities to integrate these technologies into information that they can use and better policies for management. So Professor Sanders is with the UCI Department of Civil Environmental Engineering and also Urban Planning and Public Policy. He received his PhD in civil engineering from the University of Michigan. And his core interests center around long water wave dynamics, notably floods and tidal dynamics along coasts. He's interested in advancing knowledge and models in the context of interactions between the built environment, natural environment, and human activities. We're so honored to have him with us this evening to tell us about the flood threats that are rising in the LA basin from climate change. Everyone, please welcome Dr. Sanders.
Thank you. Thank you for the nice introduction. So I'll jump into my slides here and see how we're doing here. Hopefully we'll be operating here properly. I think we probably want this. Is that what we want? Or do we want, let's see. This is probably what you want, right?
Pretty interesting.
Okay, can you see the picture now?
Yeah.
Okay, great.
This is a story map, right?
No, this is just going to be a PowerPoint presentation.
Well, right now we're looking at your browser tabs with the flood risk.
Okay, let's try it.
Yeah, but that was a really interesting map, that was.
Yeah, so I've shared, I can throw that map into the chat so everyone has access to it. And I'm going to try one more time to share.
Because you did it before.
Yeah, we did it before. We're gonna get there. It's just gonna take us a second. Okay, so now I'm sharing.
Oh, okay.
My PowerPoint. Whoops.
You just stopped sharing.
Oh my goodness. I think I need another cup of coffee. Okay, I'm gonna do that. And now I'm gonna do full screen. And now do you see like all just one picture, or do you see like a lot of little things?
Just one big picture. You're in slideshow.
Okay, great. So I think we're where we want to be. So yeah, so this is a opening slide here, a picture of one of the bridges going over Los Angeles River, waves going by, and this is from a photographer in LA. His name is Kevin Brake, and he has a studio along the LA River and has taken some pretty cool photos. I've also included some lines from a song you probably have heard before. Yep. And kind of basically, we have a challenge with flooding getting worse. So this work was done as part of an interdisciplinary team. A lot of people contributed to this study, and they're from UC Irvine and University of Miami and UC Riverside and UC San Diego. So we're based at UCI, and I work here in this new interdisciplinary science and engineering building, and that's where we sort of do most of our work. But we are interested in flooding because, as was mentioned in the introduction, it's becoming really one of the biggest challenges, facing the world. Extremely disruptive. Big flooding disasters are becoming more frequent. Events like Katrina, Harvey, Ida, Ian, and many others, Sandy. And the United States is actually leading the world in being home to the most expensive disasters happening anywhere in the world. So the top 5 most expensive disasters that we've had over the last 20 years have all occurred in the United States. And cities have been caught off guard. The flood events have come in, more intense, more widespread, deeper than really what anybody would have imagined. And the consequences are serious. We're seeing for decades we were seeing declines in flood losses. We were seeing each year fewer and fewer people were dying from flooding. We were seeing, obviously, losses were increasing, but deaths were on the decline. And we pointed to improved early warning systems and timely forecasts and so on. But there's indications now that trend is reversing. Ian just recently, as it rolled through Florida, caused quite a number of fatalities, well over 100 fatalities. And the victims are often trapped in their own homes, trapped in structures, unable to evacuate due to existing health ailments, different medical needs. They're unable to leave because they might not have the mobility they need to leave. They might need certain types of medical equipment that they can't take with them. And so that's one of the reasons why, or one of the vulnerable communities we think about when we think about the impacts of flooding. And also, the impacts of flooding have not been distributed evenly across the United States. Poorer and more disadvantaged communities and communities of color have been disproportionately impacted by these flooding events. And then we've also seen that flooding recovery has not been uneven. More affluent communities that are impacted by flooding tend to bounce back. Homeowners in those areas tend to get insurance and are able to rebuild. Oftentimes they have a job where they're able to work remotely and keep up their work and stay on top of their recovery around the house or take some time off. But more disadvantaged people often lose their job because their job just goes away. Their business is no longer in business. They don't have a job anymore. They don't have income, and they're reliant on assistance. And so these more disadvantaged communities sometimes never bounce back. So they sometimes just sort of spiral into sort of a even worse situation than they were before. And globally, big flood events are disrupting supply chains and having global ramifications. Increasingly, our transportation infrastructure is generally located near waterways because that's where there's access to trade. And so when we have transportation infrastructure built out along rivers and coastlines that are exposed to flooding, then these big flood events shut down. And that's a big issue for Southern California because we have the largest container terminal in the United States in the port of Long Beach and Los Angeles. More trade goes through there than any other port. Container trade goes through there than any other port in the United States. So the UC Irvine-led team, we came in with an interest in flood risk with these drivers in mind. The fact that flooding disasters were becoming more frequent, that cities were especially vulnerable and seemed to be underprepared, that impacts were not being spread evenly across the populations, and that communities were experiencing prolonged and incomplete recovery. And there were global consequences in terms of supply chains being disrupted. So a question that's really important to ask is what's driving these trends? Why are we seeing things getting worse? And I think our conversation opened up with a comment about climate change, and climate change is last on my list. And it's not that it's not important, but I think there's so many other factors which are underappreciated as drivers of this problem. The most important driver of this growing flooding crisis is development in high hazard areas. We sat here, for a few moments before the presentation and looked at all the housing that was going in along rivers and in low topography. And that's precisely what we're seeing around the world. Cities are trying to grow. They're trying to make room for more people. And the only land left to build in is the land that was least desirable decades ago when building took place. And now it's being revisited, or communities are saying, well, we'll have to use this land for housing too. but that puts more and more people in harm's way. Another thing that's happened is that we've marginalized a lot of the natural buffers that protect us from flooding. Examples include, coastal wetlands, for example, on the Gulf Coast, that can coastal marsh and wetlands that can buffer the impacts of storm surge. Areas where there's grasslands or forests that can buffer the runoff from mountains. So a lot of these natural buffers that we've relied upon to sort of dampen the impacts of floods are being marginalized and reduced and no longer offer us the same protection we once enjoyed in the past. A third really important driver is that our infrastructure is aging and is under-designed for the growing concentrated runoff that we're seeing. In many cases, it's under-maintained. So without adequate investment in flood infrastructure, we're seeing, failure of those systems, or they may be just simply undersized. Hi, kitty cat. That kitty cat has joined us for the evening. Another thing that's been an issue for cities is that our risk mapping in cities has been inadequate. By policy, the federal government maps two types of hazards. One is riverine flood hazards, and the other are coastal hazards, but it isn't required to map what do we call pluvial hazards, or just rainfall flooding hazards. And in a city like Los Angeles, blanketed in concrete for miles and miles, when rainfall hits the ground, a lot of runoff is generated and it pools and can create a hazard. But that's not required to be mapped. Another factor is what I call compounding social factors. So a flood event happens on top of an existing housing crisis or unemployment crisis, and it just seems to compound the existing social inequities we already face. Another one is complexities of governance. It's really, you guys really appreciate how complex our governance is. We have, city level government and county level government and state level government and federal level government. And within each of those governments, we have many different agencies and contacts and divisions and groups. And in order to manage these flooding problems, all those groups need to interact, and we can't necessarily say that that's a smooth running machine. So that's another reason why we're seeing growing flooding problems. And then last on my list, and certainly not insignificant, is the role of climate change. We have a warmer atmosphere that holds more water. We can see more intense downbursts. These tropical storms seem to be becoming bigger and more intense. And so that's a driver as well. And along the coast, of course, sea levels are slowly rising and threaten increased coastal flooding in the future. So these are kind of the big drivers. And I think my message to this group is in terms of some of these growing climate stresses, it's more than just climate change. It's a lot of things that we do in terms of getting in harm's way, marginalizing the natural buffers, not maintaining our infrastructure. And we have to be careful not to sort of attribute all of these problems to climate change. Okay. So with this as a context, we've developed this detailed flood simulation, capacity, which allows us to look at entire mega cities and resolve flooding, at fine resolution. And this is especially valuable because it allows anybody to kind of immediately grasp, where and what might be impacted by flooding. And we can update these maps based on different climate scenarios that we think might happen in the future. We can consider different types of infrastructure investments, and so we can really start to sort of create a platform that's intuitive and visual and quantitative and informative. And research has shown that this type of sort of tool is really valuable for bringing sort of diverse groups of stakeholders together to think about a problem and figure out how they could find some common ground and move forward. So in the past, there's been, you probably are aware that planning flood infrastructure, a lot like highways, is really a divisive issue for communities. And so sometimes those conversations can just spiral and not be productive at all. But what the research has shown is that if you sort of use the best available climate information and the best available models like this, and you start looking at what's most likely to happen, what could happen in a realistic way, then it produces a more productive sort of conversation. And in contrast, this is the mapping that's done by FEMA. We were sort of looking at it recently. It's a classification approach which says these are areas that are in flood zones or not in flood zones. They use somewhat cryptic designations like Zone A and Zone AO and Zone X and Zone V, and sometimes it takes a whole lot of work to figure out what they even mean. So they're not very straightforward. Also, the maps get updated really slowly. And as I mentioned earlier, the FEMA maps aren't designed to account for rainfall flooding. They're only designed to account for sort of the possibility that streams, channels can't contain the flow that they were designed to hold, or along the coast that there's a high tide or a wave event that could cause coastal flooding. Some of these maps correspond to a designation called areas protected by levees. So if you look at this light brown color in the middle, that's an area designated as an area protected by levees. The lighter purple is the 500-year floodplain, and the darker color is the 100-year flood zone.
Those levees are going to be along the rivers, I think, because I see the LA and San Gabriel River running through there.
Yeah, you can see the river pass in there.
And
So the research questions that interested us with this sort of broad national context and also local context, we could legitimately ask, how severe is the flood risk issue in US? Exactly how many people are exposed? Because if we're not mapping the pluvial flooding, we don't really have a good handle on what the flood exposure is. And also, who's exposed? FEMA actually doesn't even do exposure calculations. They just map, areas that fall within flood zones for the purpose of running an insurance program, so they can support, flood insurance. But they don't think about exactly how many people are exposed. And oftentimes, when states and communities reach out to the federal government for assistance on flood control projects, the most important factor that's considered in those projects is the costs of a flooding disaster in terms of damages. So they don't actually think about people. The sort of metric that's used to justify resources oftentimes is, well, will your project reduce the losses, the financial losses of a flood? They're not asking, will your project improve the livelihoods of the people who live near that project? That's not really part of the picture. So our research questions are, how severe is the flood risk facing cities? Who is exposed? And then, can local, state, and federal governments improve infrastructure planning and community assistance, with access to some more, better data? And so we focused on Los Angeles. You can see here this nice little photograph of downtown Los Angeles and the 110 freeway. Los Angeles is the second largest city in the United States. It's the third largest metropolitan economy in the world. There's around 14 million people living on the coastal plain between the mountains and the ocean. And it's an area with really low levels of awareness and preparedness relative to flooding. I think we think about a lot of different hazards in California. We think about earthquakes. Increasingly, we think about fires. We're caught up in drought and water scarcity. We don't think a lot about flooding. And so if there was a flood, I think we'd encounter a really low level of preparedness. Some examples of flood events in the past, you probably have seen these photos before. This was, I think, the 1938 flood that damaged, a railroad bridge in Los Angeles, caused flooding in the region, and even caused inundation and sort of water and mud to flow across Venice on the way out to the sea. So this is a city with a history of flooding, and in fact, the channels we have today, these flood control structures we built today, were approached to really, literally try to control the flood. Keep it within these armored systems. We built these. Almost took like a wartime approach to flood defense as we built these systems after World War II when building out, flood control systems, much like fortresses with a lot of concrete and hard surfaces to try to defend against these really forceful flows of water that came from the mountains and rushed down to the sea over a pretty steep slope. And we used like these nice sleek designs to move water really quickly. At that time, Mulholland had brought an abundant supply of water to Southern California, and people wanted really an environment that was good for, a stable environment that wasn't disrupted by extreme events. And so the priority for the design at that time was to get water as quickly possible out to the ocean and to maximize the amount of land that could be developed for housing and for businesses and for industry. So we use these really sleek designs to bring water down to the sea. And we see those all the way down towards the coast. But these systems also divided communities, kind of just like major highways. And they left out features that you'd find in other more natural systems, important features like, are there trees that offer shade? Do you have any soil that could soak up the water and recharge the groundwater basin so that we would have a groundwater basin that was naturally, filled up with water every winter? Could you have, ecosystems along the river that integrated into your terrestrial ecosystems? And another thing that we stopped was the movement of sediment from the mountains to the coast. And at a time when sea levels are rising and land along the coast it's low lying, is vulnerable to inundation, it would be really, really valuable to have more sediment flowing down to the coast to sort of help coastlines be more resilient to future flooding. So we're left with this infrastructure that was designed for a different time, and it's creating sort of challenges today. And one of those challenges also is that housing was all built out in this lowland topography, and now these areas are highly dependent on that infrastructure to perform as designed, or else they face really serious flooding. This is a community in North Long Beach that's sitting lower than the height of the levees that protect it. So if water were to spill over the levees, it would just run into these communities. And so now if we sort of step back and just think about the Southern California basin, as I'm showing here, we have something around 18 million people living in the LA metro region as a whole. The populations are clustered in these lowland plains, these coastal plains and inland plains below these mountains. We're surrounded by mountains, so when the rainfall comes and strikes these mountains, it runs off very quickly with a lot of sediment and debris. And another dynamic we're watching now is the dynamic of wildfires. And with the wildfires, they strip the mountains of vegetation and they turn like the soil to be really water repellent. And when that happens and a rainstorm comes, a lot of water runs off really quickly and a lot of sediment runs off too. And so to deal with that problem, we have these debris basins all around the mountains to try to catch the sediment. But as those sediment loads get higher, they quickly get overwhelmed, and our flood control systems are quickly choked with sediment. And once the channels are choked with sediment, they no longer meet the design needs that they were built for. Also, along rivers, people have rightly said, boy, this river no longer offers the sort of any ecosystem support, and we ought to have, vegetation and plants and things like that in the river. Well, we can do that, but when we do that, we also reduce the capacity of the channel. So if we want to basically build in our own river channels and add vegetation and plants and sediment, then we're accepting a trade-off, and we're saying that that's going to reduce the flood capacity of those channels, and it's going to make it more likely that people experience flooding when an extreme event occurs. So this is the broader context of Los Angeles, why Los Angeles is sort of an area that's of great interest in thinking about flood risk. Another issue to be aware of is that its main infrastructure has already been sort of assessed, and weaknesses have been documented. And when we came out with our study, it was a big concern to me that we not exaggerate the sort of the potential risk facing the region. And so we carefully reviewed other studies that have been done. And this map here shows channels color-coded as to whether or not they're able to contain a 100-year flow. These red channels here, Dominguez Channel and Compton Creek and part of Los Angeles River, several independent studies have already concluded that the channels are too small to contain a 100-year flow. And so that's been independently verified. Also, the Army Corps does sort of assessments of the condition of the channels, and many segments of the drainage system have been assessed to be in unacceptable condition due to concrete that's spalling and falling apart, or fractured, or gaps in flood walls. A lot of different sort of repairs would be needed to even get it to perform as we would want it to perform in an extreme event. So the point is that we live in an area with some dynamic changes taking place, with loading from the mountain mud and debris, and channels that are aging, and sort of policies that have not required that we map flood risk in the past. So pluvial flood risk. So we sought to sort of answer these research questions by building out a really detailed flood hazard model. And this is a very innovative model. This type of modeling has not been done for this scale of modeling has not been done for any city in the United States or the world. This was new. And we wanted to simulate flooding from pluvial, fluvial, and coastal drivers. So pluvial is a rainfall flooding. Fluvial is the risk that the channels overtop due to the channel flows that are larger than what can be contained by the channels. Coastal flooding is high tides and along the coast. And then we wanted to estimate how many people are exposed and who is exposed. And so for every land parcel in the county of Los Angeles, we estimated the flood depth, we estimated the population for each land parcel, and the population fractions by race and ethnicity. And that was done by taking block group census data and sort of then projecting it down to each individual parcel. We also wanted to say something about, well, what is the capacity of these communities to be impacted by flooding and to recover? And so to do that, we also used a couple of tools that have been, one tool has been developed before and used before, which is called the Social Vulnerability Index. It's an index that's supposed to provide some guidance as to whether a community is more or less vulnerable to a natural hazard. And we introduced a new index called the Neighborhood Disadvantage Index, which is an index that's meant to sort of measure the sort of socioeconomic capacity of a community to recover and to manage the consequences of flooding. So just a little bit different. And then we studied the distribution of exposure at city scales and also for the entire region. A little bit about the details of our method. What made our methods quite innovative is that we overcame some of the bottlenecks trying to represent detailed infrastructure in a region-wide fine resolution flood model. So what I'm showing on the right-hand side is a picture of one of the east-west moving freeways in Los Angeles. And it's an example of how if you were to fly a sort of a survey from above and look for the ground elevation, you would basically, the ground elevation at these locations would be sampled based on the freeway. So if you had an airplane with a laser pointing downwards to measure the ground surface, that laser would strike the top of the freeway. But what it would miss is the pathway for floodwater to go underneath the freeway. And that's what we did in our methods. We processed a lot of street data and terrain data to try to make sure we captured important flow paths that would be needed to sort of reasonably represent the flood risk across the region. Another example of a flood sort of pathway is shown in the left-hand side. There is a flood drainage channel right here that goes underneath a freeway interchange, and then it pops out over here. So all that is a subsurface culvert connecting one open channel to another open channel. And so once again, we relied on county provided data on the drainage infrastructure to make sure that our model had a flow pathway in it from this point to this other point. So we took steps basically to represent the infrastructure in ways that hadn't been done before in large scale models. Now, this type of infrastructure is routinely represented in small scale models. So if you built a model, if like the city contracted with a consulting firm to study a reach of Ballona Creek or a small reach of Los Angeles River, they would routinely account for this type of detail. But this type of detail is very difficult to account for over the scale of an entire metropolitan region, which is what was innovative about our work, is we sort of approximated that effect at really large scale. And voila, this is our map, sort of artistic map of the 100-year flood zone across the Los Angeles, Orange County coastal plain. You can see the mountains on the north and the flow pathways. The solid line right down the middle is the Los Angeles River going through downtown, and then South Central and towards Long Beach. Over here, we have the San Gabriel River coming out of the mountains. This is the famous Whittier Narrows Dam, which I understand is that's the highest among the Army Corps ranking of risk. That has the highest risk rating of any dam in the among in the region, and it shows sort of the detail and spatial extent of our model. We also have sort of our estimate that in a 100-year event there'd be around 425,000 people, around $56 billion in property exposed to flooding greater than 1 foot in depth. Now, if you were in a property and your property is higher than 1 foot in elevation, then you would likely be able to ride out that event from a property damage perspective. But it would depend on your you'd have other impacts in terms of exposure to water and challenges getting to work and contaminants being moved around in the water, and it would be a mess. So we also, in this study, focused on different drivers of flooding. This map shows the pluvial, fluvial, and coastal distribution of flooding. And the pluvial one is the one that I mentioned before. It had not been previously mapped. And previous mapping focused on the fluvial and the coastal, but not the pluvial. And when we did that, we saw that the exposure associated with pluvial flooding was actually larger than the other two combined, and also far larger than the population and property contained within the existing FEMA flood hazard zone at for a 1% annual chance flood. So the 100-year, the 1% annual chance flood hazard area, according to that FEMA developed, contained a population that we estimated to be around 23,000 people. And as I was mentioning, our overall exposure estimate was around 400,000 people. So vastly different numbers in terms of the scale of the exposure. Okay. So any questions so far?
Well, I had wondered about the 100-year flood hazard, but you just answered it. It's a 1% annual chance.
Right, that's
which
right.
Doesn't mean that you're going to get it 100, like that it only happens once a century, because in Texas, haven't they had the 1% annual chance of the flood 3 times in the last 5 years or something like that?
Yeah, and so 1% annual chance means that the likelihood of an event of that size or larger occurring any given year is 1%. But there's nothing stopping nature from producing 2 events, back to back. It's just based on the historical statistics for a region. Then you kind of look at the severity of event and you characterize the sort of frequency with which an event of that size or larger occurs. And then in some places, due to sort of a changing climate, the events that are a 100-year event today may only be, a 50-year event 10 years from now, because, if the climate's changing and becoming warmer. So sometimes, saying we definitely don't want to say that these events happen like clockwork every 100 years, for sure.
Right. And then, so the 0.2%, some people also call it the 500-year flood, but
Correct.
that's not quite it. Can you translate it into rain rates?
Yes, I don't have the rain rates for you, but our pluvial scenario was based on rain rates provided by NOAA's Atlas 14, which provides rainfall intensity data for the purpose of flood studies. So you can go to NOAA and ask, what's the rainfall intensity of a 1% annual chance event and a 0.2% annual chance event, and those data are provided.
And that's really important because weather satellites can measure, they have microwave sensors that can measure rain rates. So you can get, if you know what the rain rate is that will get your region in trouble, you can also watch, follow NOAA's, NOAA on Twitter when Twitter was still viable, but you would know that, oh my gosh, I better pack my to-go bag.
Right. Yeah. So we've also done modeling based on observed rainfall, not for this area because we don't have enough big storms to sort of see a big enough flood signature to try to model it and validate the model. But we've done it for places like Houston and Miami, and so we published papers on the accuracy of our inundation modeling in response to sort of observed rainfall and forecasted rainfall, as an example.
So when you did the mapping, of the freeway overpasses and stuff, you bought LiDAR data from airplanes, and then you put that in your model for the height?
Yeah, we didn't have to purchase the data. The data was publicly available, but it was a previously published aerial LiDAR survey that had topographic heights gridded at 3-meter resolution. So we used their previously published digital elevation model data derived from LiDAR, and sort of there's also quite a bit of data processing that goes into those digital elevation models. They try to do some smoothing. For example, there'll be buildings and other features on the land surface that need to be filtered out. So quite a bit of work goes into those digital elevation models.
My question is, who is your audience? Who have you provided this information to? You mentioned all the agencies that are potentially impacted in local, state, federal. So who have you shared this information with?
Yeah, that's a really important question. We reached out very early to a number of different groups to try to have input that could help us shape our study. And with the funding from the National Science Foundation, we were able to do a series of focus groups that allowed us to meet with, first of all, community groups, sort of local community groups across Los Angeles that were working on water projects. That was hosted by the Los Angeles Area Regional Climate Collaborative, or the LARC, out of UCLA. They hosted us to connect with community groups. We had another meeting early on with the flood control districts of both Los Angeles and Orange counties to let them know we were working on this study, and ask for their any input or suggestions. And at that time, we shared some preliminary results that were actually more severe than what we finally converged upon in our final study. And then we also gave a presentation to statewide flood managers, so that statewide leaders were aware of our study and had the chance to provide some input. So we tried to be as transparent as possible that this work was moving forward and that we would be open to their input, and then we proceeded and have since had a number of different with the paper coming out. I've had subsequent meetings with the County of Los Angeles, Department of Public Works, state agencies. So I'm not sure if how much more you want me to share about that, but we've tried.
Do you have any more stuff prepared? And Kathy has a question.
What's the question, Kathy?
Oh, you largely answered it. It was back about the 100-year flood, And it's, okay, so it's the 1% annual chance. But in terms of sizing facilities, you've got to define what it is. So you have to have a data set of some kind in order to size facilities, right? The storm channels and those kinds of things, and to make some estimate of.
Yeah, the 100-year events were like we used the NOAA data to figure out the rainfall rate for a 100-year event, or 0.1% annual chance, and we analyzed data from 55 different gauges. All these little green dots are stream gauges that are maintained by the different utilities and Department of Public Works and flood control districts and watershed units. So at each one of those gauges, there's a record of flow measurement. And so we analyzed the records at all those gauges to try to estimate what a 100-year flow means at each space, at each location. And then we added that to our model to try to capture that level of flow and see, first of all, if the channels could contain that flow. And then secondly, if it's not contained, where does the water go? How does it move across, spill out over the channels and spread out, and where does it collect, and who would be impacted?
So the data sets that you got from NOAA, though, what time frame do they represent?
They're supposed to be representative of today's rainfall intensities, today's extreme rainfall intensities.
So they capture that.
Yeah, right. So they're designed for precisely what we have done here, which is to say, if you need a design, if you need to look at the possibility of a 1%, flooding, 1% annual chance event, they're offering the rainfall rate associated with that 1% annual chance event. And it's a spatially distributed parameter. So it's different on the mountains compared to the coastal plain. And
Okay, Kathy Berlin has had her hand up for a long time.
Thank you. I have a specific question because I have a specific interest in the Santa Monica Bay.
okay.
Did you, in your modeling, I can't tell from these maps because they cover such a large area, did you model how far inland the water would go in like Manhattan Beach and Hermosa Beach, at the beach cities?
Yeah, we tried to. We simulated a sort of a storm tide scenario where the water level rises up along the coast and inundates sort of coastal low-lying topography. Now there's a certain level of infrastructure that is difficult to capture in a large scale model like this one. Small little local flood walls, and which I know, for example, around Long Beach and Belmont Shore, there's little flood walls that we may not have captured, in our model, but that was the intent, to try to get basically the risk of water, high tides backing up and inundating low-lying areas, and also the possibility of stream flows coming down and rainfall coming off the watershed at the same time.
So is there somewhere where I can list an address and it will tell me at what level the water will reach that address?
Yeah.
And
Yeah, I think I could I think I shared already, but I could share again, like
The story map?
is the story map allow you to add an address?
I don't know. I don't think so. But did you see, Kathy, how from the LA Times article, they put his raster layer on the map box, and so you can explore it like I'm doing right now. You could really zoom in. And I showed you Manhattan Beach. Manhattan Beach, because of the high cliff over
Right.
there on the Strand, because of the high cliff, there isn't really any risk, but due to the coast. But there is along Valley Ardmore, that's the pluvial flooding.
that makes sense given the topography. Yeah, thank you.
But this is what I worry about, which is that in Torrance, the area, the Torrance Memorial Medical Center, which is a regional Cedars-Sinai affiliate hospital, that is a flood prone area, as is, there's a refinery right next to it. So
Yeah.
If the refinery floods, you're just going to have a mess of hydrocarbons. You're just going to have a
Yeah.
mess of hydrocarbons, and you're not going to be able to get to the hospital.
What
So
about the
that's-
refinery in Manhattan Beach that just had a fire? Is that in the flood zone as well? It seems like it.
Oh, no, it's not in Manhattan Beach, it's in El Segundo, and that's on a high cliff.
You're right, it is in those.
These are really important, I think discussions to really think about consequences and, alignment of, because in flooding, when people do flood risk assessment, oftentimes, they're lacking a lot of this sort of connections between like where are the hospitals and where's the sources of pollution that could immediately flow into, what I mean? What you just said, Grace, I thought was a really good observation. And
Hydrocarbons?
yeah, I mean, just think about all of the industry across these lowland areas that will be washed, like the water is going to wash across and pick up a lot of contaminants and toxics and spread it all over. Sewage systems are going to be completely flushed out, and there'll be viruses and all over the place. So these are real concerns, and it'd be worthwhile, I think, to kind of try to raise awareness about some reasonable things that could be done to try to manage those risks, making sure they have some kind of some plan in place to try to manage it. But I should probably keep going. I'll be here all night. I've got quite a few
Okay.
more
I
slides
thought you
to
were
go.
done with your prepared
Oh,
slides, but
yeah,
I will stop share and let you go share. I'll let
Yeah.
you share again.
I thought I was sharing still. No?
No, you are sharing.
Okay. And then I did put into the chat like an ArcGIS data viewer where you could punch in an address, and I know we have an address and that has a bunch of different layers of data that we use to kind of play around with the look at data.
Thank you.
Okay, so I'm going to keep rolling along here. Now I'm going to move into the equity work that we did. So what I've shown so far is really the scale of the flooding, but now I want to talk about the equity. And the tool we use to do that is something called a Lorenz curve. Okay, and a Lorenz curve is a tool out of sort of economics. And the basic idea is that it's a tool to test or to measure, is wealth evenly spread across the population or unevenly spread across the population? And the world we live in, wealth is unevenly spread across the population, right? And so this curve here that I'm showing is basically you have imagine a population of 100 people, okay? And so you go from 0 to 100% of the population on the x-axis. And each person has a different amount of wealth. Some people have more, some people have less. But if you sorted it so that the person with the most wealth was on the right-hand side, and the person with the least wealth was on the left-hand side, and then you plotted the cumulative wealth across the whole population, you would see a curve like this one, where as we start off on the left-hand side of the population, this is the side of the population with less wealth per person. And so it starts off with a relatively mild slope. And as we get to the right-hand side, the slope gets steeper. Okay, so the key thing here is that we're looking at proportion of the population, and we're looking at the proportion of the wealth after we sort the people according to who has the most wealth. And if there was an even amount of wealth across everybody, you'd see a straight line. So economists introduced this idea of a line of equality, and then the area here representing an indicator of the inequality. And that's known as a Gini coefficient. So the area that's shaded there between the dashed line and the solid red line is a measure of whether, a measure of inequality. So this is used in economics, and we wanted to then use this in our work to look at flood risk. And so we went ahead and moved on to flood risk, where instead of now the y-axis being the proportion of the wealth, we now have it the proportion of the risk. And instead of sorting the population by wealth, we can sort by a lot of different things. We can sort by income, we can sort by the property value, you can sort by the fraction of the population that's white or the fraction of the population that's black or Hispanic. And we can also sort by the level of disadvantage. And so we sorted in many different ways. So I use this variable V to be my sorting variable. And with that, we can then measure, to what extent do we see disproportionate risks across Los Angeles County in accordance with these different sorting variables? Which variables say something about the disproportionate risks? And I'll point out that sometimes the curve goes the other way. So if the curve goes the other way, what that means is that there's a disproportionate underexposure to the risk. So that would mean that with that variable, it was associated with less exposure than average. Okay, so are we ready to dive into a bunch of Gini coefficients?
So that's fascinating. So a higher Gini coefficient means higher inequality, right?
Right, that's correct.
So 0 means it's perfectly even.
You're one step ahead of me. Yes. So
Okay, all right.
the Gini coefficient goes from -1 to 1. So 0 value implies a proportional exposure. Positive values suggest sort of a disproportionate exposure or an inequity for higher values of the sorting variable. So if the sorting variable is say, the fraction of the population that's Black, and you saw like a bigger positive value with a Black high Black population, then that would be an inequity associated with sort of the Black population, as an example. Then the negative values suggest less than proportional exposure. Okay, so we did this for a bunch of different variables. This is the population density across the region. So that scales how many people are in different places. We have the property value map here showing more expensive property value in the core and less expensive in the greener areas. We have this new index called the neighborhood disadvantage index, which is where people have higher levels of socioeconomic disadvantage. And so we see higher socioeconomic disadvantage in the sort of central areas. And this is the vulnerability index developed by University of South Carolina. And over here we have different racial and ethnic population fractions. So the sort of Black population fraction is highest in this area like Carson and up towards Hawthorne. You can see the different distributions for these 4 different racial groups. And there were others, there's other sort of racial ethnic groups in the census data, but we didn't include all of them because the population numbers were pretty small in some of the other ones. Okay, so these are now the Lorenz curves for each different flood hazard, the overall flood hazard, which we called composite, and then the pluvial, fluvial, and coastal hazard. So the first thing we noticed is that with the rainfall flood risks, all the lines were not too far from the line of equity. So rainfall tends to impact people somewhat equally, although the Black Black tends to be an indicator of a weak inequality. And sort of the white population fraction tends to be an indicator of a weak, weakness, or weaker, less proportionality. So sometimes it's hard to even talk through these words. But the strongest signal we saw was with fluvial flood risk. As I'm showing right here, that this Lorenz curve departs a long ways from the line of equity when we sort by the non-Hispanic Black population fraction and we look at fluvial flood risk. So that means that this data is saying that communities with larger Black population fractions are disproportionately exposed to fluvial flood risk. Another indicator is down here in the lower right-hand corner with coastal flood risk. You'll notice that non-Hispanic whites populations are almost exclusively exposed to the coastal risk. So the 2 strongest inequalities in the data was that among the riverine flood risk, communities with larger Black populations were disproportionately exposed. And along the coastal areas, white populations tend to be disproportionately exposed. We also did some socioeconomic disadvantage. I'm just going to skip ahead because it's I feel like we're going through a long night here. But
this is fast. This is really fascinating because this is where the audience lives.
yeah. And so now the question is, okay, so we have these inequities. How do we make, and we have all this really detailed data, how do we make this useful to communities and to governments so that, you know, we can try to manage the flooding problem and take some steps with infrastructure investments and so forth. So we went ahead and took this parcel level data and we aggregated it at the municipal level, which is the level of sort of the city. And each one of these bubbles here in the left-hand side is a different municipal government in Los Angeles County. And the size of the circle represents the size of the population exposed to flooding greater than 3 centimeters. So we used a lower threshold for this graphic. Okay. And on the right-hand side, so you can see the spatial distribution. This big circle here is Los Angeles. Los Angeles is obviously the biggest city, so it's not surprising it's the biggest circle. But down here, you'll notice Long Beach is a large circle as well. And when we look over here on this diagram, and this is meant to sort of, you know, serve as a tool to help understand at the regional level which municipalities face the most severe flood risk, and also which municipalities would face the sort of biggest socioeconomic disadvantage trying to recover. So the size of the circle represents the number of people exposed. So Long Beach has a really big circle. Some other big circles are Los Angeles. This other big circle is in unincorporated Los Angeles. And then there's some circles here like Paramount and Southgate, which are sitting up high. And the height of this diagram is the average flood depth for the parcels that are exposed. So the fact that Long Beach is sitting up high means that it's facing an average flood depth close to 1 meter among the parcels exposed. So that's a really high hazard. But then on the x-axis, you see what we call the neighborhood disadvantage for the parcels that are exposed. And so the further you are to the right-hand side, that means the less sort of economic capacity that you have in your community to try to recover and cope with the flooding. So that would suggest that if you're way down here on the right-hand side, you would be in sort of high need of assistance from government to try to get help to recover. And if you're on the left-hand side, you would have more affluent population that would have more resources in terms of its ability to recover. So those factors could be considered in terms of resource allocation to try to deal with the challenge we face today, which is that the more disadvantaged communities are facing a really hard time recovering from flooding. Another piece here is that these models can be run in real time with forecast data. And this is a Houston model, but it shows the idea of these detailed models being run in sort of a forecast mode, providing, you know, a forecast several days in advance of the kind of flooding that you could see on a house by house basis. So I thought I'd show that in there also, and that this sort of simulation technology isn't just useful for long-term planning and sort of resource allocation and infrastructure investment, but it can also be used for sort of emergency preparedness and response. So I'm going to wrap up now with just a couple of slides. So what have we learned? So we learned that we can now assess exposure and inequities to compound flood hazards across entire megacities, and that these intuitive visualizations offer an intuitive entry point for stakeholders to engage and think about some of the consequences. As you've done so tonight, you thought about a hospital and in a sort of a energy facility and things like that could speak to vulnerabilities. With this type of quantitative framework, we can more effectively measure the efficacy and sort of fairness of proposed solutions. So if someone comes along and says we should be raising levees, or we should invest in green infrastructure, or we need to do flood proofing, a framework like this allows us to kind of quantitatively measure how exposure would change and how inequities would change in response to these different measures. And so then we can provide these systematic measures of equity in our public investments at both community and regional scales. A little bit of context here in terms of other work. One of the things we're doing here is confirming that flood risks are underreported in cities due to this pluvial contribution. So the fact is we're not mapping flooding from rainfall across the US, and when we do, we see a much larger exposure. Another thing is that here in Los Angeles, one of the strongest inequalities, as we saw, was that Black communities were disproportionately exposed to fluvial risks. And that's actually the opposite of what's been reported in some studies for the nation as a whole. So it kind of shows that on a city by city basis, the inequities can be different than what they are, say, for the nation as a whole. And the work also shows a contrast in sort of the racial and socioeconomic inequalities between riverine and coastal flooding. The riverine flood risk is impacting a more disadvantaged community, and it's impacting communities with large Black population fractions, and also Hispanic population fractions. Whereas the coastal flooding is a challenge, it's impacting more affluent communities and also more white communities. So I guess my final remarks here are that across the U.S., flood infrastructure is aging and needs investments. The demands on infrastructure performance are growing. In the past, we designed flood infrastructure for one thing only, which is to manage the flood. And now we want flood infrastructure that offers benefits for ecosystems, for water conservation, for water quality, to address climate change, to offer urban amenities. And so it's more complex, the type of design and engineering we need to do. But these simulation technologies, I think, do offer a platform to think about these risks, contemplate the impacts of different decisions, and try to design more equitable and effective solutions. So I will close on that note, and thank you for your attention.
That was really